Okay. All right, so now we're cabled in, and we're about to be able to go. We're going to use the directional coupler here, and what I have is these two 908A loads. I have a little T and the short, and the short we're going to use as the reference point for setting up the reflection measurement. Now, what are we going to measure, and why do I have the two loads? Well, what I have here is, let's see if we can get that in just a little math here. Basically, what I'm going to go do is I'm going to take these two loads and then screw them together. Thank you. So that now what we have are the two loads effectively in parallel, which drops their impedance to 25 ohm.
Okay. Oh yeah.
So
big difference.
Yeah, you can actually get known VSWR stubs that'll, like terminations, that'll have a known characterized things like this is a 2.2 to 0 or like a 2 to 1 or 3 to 1 or whatever sort of thing.
Well, you still good at home standard though.
Yeah, because these things are pretty accurate. So it'll come out somewhere around 2-ish.
But once you know your reference, you're good to go from there on.
Right, right. And if I really wanted to get an accurate SWR, I would use the. I actually have a proper 85032E kit, and then I have with that, and then with the VNA that I have, or with the directional couplers and a power meter and my 8400 sensors, I would actually be able to set that up to get the exact reading and that. Anyway, so if we take a look at the little math for it, basically, the reflection coefficient value is going to be the load minus the system impedance with the load plus. Now, the system impedance 50 ohms, and because these are going to be in parallel, that'll give us 25 ohms. So if we do that math, we get a resultant coefficient of 0.3 repeater.
Sure.
Now, the formula for the VSWR is basically 1 plus the absolute coefficient, 1 minus. And that results in a VSWR of 2. And if we look at what our return loss should be based off that coefficient, we should get around minus 9.5 dBm on the return loss.
Okay.
So knowing those figures, we now have some idea what we'll see coming out of this. So the first thing I want to do just to show this is just going to turn on the output of my the output of my 8340B. And what you can see here is we're reading. Let me.
What are your settings on the 80B?
This is it's continuous wave, 0 dBm, 100 megahertz. So we're right at the bottom of the thing, but it is what it is. And my 8340B hasn't been leveled properly. I have to get in, and I fixed it up so that it basically works across the frequency range.
I love this right here because it has the log part.
Yeah, well, now you're reading it in dB microvolts, right?
Well, I'm saying it's easy for me to think because I know everything is microvolts and millivolts, and most of the things I deal with are dB, but it makes me mad because I always get dB, dBc, dBms in my head confused. So I'm just thinking it's all millivolts though, right? Microvolts and millivolts.
Well, it's that system impedance. You got to know that to be able to convert back and forwards between them and so on. But anyway. If I go over here and I press the power measurement, you'll see that we're reading 6.4 microwatts. And if I tell it to display that in dBm, I'm now getting minus 21.9 dBm. Now, the reason I'm getting minus 21, even though it's set for 0, is because of on this directional coupler, basically on each coupler, you'll get a 20 dB loss.
Gotcha.
Now, if you want to actually just pass me that clipboard over there.
Yeah. I don't want to drop my fingers.
Yeah. So what you can see here is this is actually a test of the directional coupler. And if you were using this in a real test environment, you'd know exactly what the
frequency and
how much am I losing on the transmission line, on the strip line through it. What is the incident at that frequency really? It's going to be minus 21 instead, or minus 20.4 or something. Right. You'd be able to take that and then add that to your specs or to your measurements, if you wanted to do it that way. So what we're showing here is that we're at minus 21. Now, I can actually also turn on B, and what we're now seeing is that I'm getting minus 22.1, and what that's showing me is that that signal has come down here, hit this endpoint, bounced back, and I'm reading the reflected information back off there. There's a similar connection to this at the other end of this directional coupler. If I pull that across a little bit, that you can see that will show that's the incident. That's where I'm reading that 21.9 from. So that's the show me what I'm getting there. Now, I want to measure that SWR. So that's a reflection measurement.
So in this scenario, this would be a good, if you had your UT at the end of that, get all your references, and then you put your UT at the very end of that.
Right, and that's exactly what we're going to go do here. So what I'm going to go do is come over here into my reflection measurement, and I'm going to start with SWR, and so I want a short. I'm going to put my short on, and then I'm going to save my reference. Okay, so now that I've done that.
And the 3 slashes were the indication that it took its reference, right?
Yeah, because we're measuring SWR, it's saying like it's 150. Yeah. So on, if we were to go back and measure absolutes, you would see the millivolt and so on. So now I can take this guy and I can drop this guy on.
Tell my wife, we're going to hang out, Tony. We're going to talk geek and drink.
And so there you go. You're seeing that we're getting 1.96-ish.
With the split.
With that. And the theoretical was 2.
Oh.
Right? So we're pretty damn close. Now I can do I can go back and say I'm going to look at my phase, and what I'm seeing is minus 9.74. This is minus 9.5.
Now you did that measurement with a short. Now if you were to take just the one of those loads, do the load measurement, and then redo it with those both, would you have a more accurate measurement?
No, because the load measurement is really designed just for. It's my doggy. Sarah's taking him. My wife's taking him out for a walk. Oh. That load, that's designed for that open reflector, the T measurement, when you do the load there. Oh. Right? It's not like a VNA where you're taking, say, a 909F, which is a very highly accurate 50 ohm load. Okay. And what you want is basically everything to be absorbed, the entire signal to be absorbed, so that you know that you've got your matched short first. Your matched load.
Took everything away.
The short is just what this system uses. In a proper VNA, you're going to use a short, an open, and a load to do your 2-port cal, right? So here we've got this phase and a magnitude that we're showing. Now, if we go back here, you can see the standard units. What I can also do is go down here to impedance, and now what we've got is we've got the impedance telling me that it's reading 25.5 ohms, and
is that deflection, the 2.8?
Yeah.
Okay.
And so now I forget how I should be able to do this And now what we've got is we've got our complex impedance here.
Oh, shit.
Right, so here's our real part, 25.4, and our imaginary part, which is what the little j is 1.23 ohms.
Okay.
So you know how we talked about that Smith chart where it goes around, right? What you would take, this is the actual complex impedance measurement.
Okay.
You would be able to take this and normalize it. Because remember, the Smith chart is basically 0 to 1. And
Is that just reactance? Is that reactance or is that something else?
Yeah, no, that's the well, reactance. You have impedance, reactance, reluctance.
Okay.
Which are the AC versions of resistance, capacitance, and
because AC is definitely different. I think,
because the AC you'll get these complex values, right, based on stuff. So.
Neat.
The
complex.
You would then take this and you would normalize the real and the things to get the position on the Smith chart, right? Okay. And that would tell you, and then you would move, but you would change the frequency and you'd move around and you would create your Smith chart.
Yeah.
This thing has a cool capability. I can go over to system load and I can hit normalize.
Oh my God.
And now it has actually normalized that that Smith chart value. So if we look at this, if you remember how the Smith chart's working, 50 is going to be in the middle. Half is basically that middle point.
Okay.
And 2 is going to be 0.02 is right. So we're reading almost a perfect sort of. No, sorry, the 50 is not going to be the middle point. 50 is going to be the 25 point. It's going to be halfway to the 1, which is the normalized, right?
Bar, but still pretty damn small.
So and it's going to be it's very close to a pure 25 ohm load.
Everything out, everything back in.
Yeah,
essentially, yeah.
And so now we've done the measurement here, and I can go measure different things, and I can look at.
Do you have a UT you can put at the end of that? Like
what's
a cap or something?
No, I actually don't have a device that I can test at the moment. So I wanted to get. I need to get a little amplifier that I can just.
Theoretically, if you were to just take that off, it'd be an open, right?
Yeah, but you're going to see. Let me pull that up. Come on.
Because, I mean, right now the number is the perfect reference, and then when you see an open, that's the measurement technically-ish.
Yeah, see, so now you're not getting 25, now you're getting 70.
Which always vary because, your RF's just coming out there like a spout of water. And
right.
I mean, this is the hardest part of RF, is stabilization. For me, it's like, there we go.
Nice. So, we can do that power measure.
It's so sensitive, though.